Hi, good morning, everyone. This is our so-called Federated Learning talk series. Today we have Duan from Chongqing University to come and talk about his work on personalization techniques for federated learning. I think to address the divergence of the local model due to the different data distribution in the local clients. So, okay, without further ado, I'll let Mo-Ming start his talk.
Hi everyone. The topic I will be talking about in this seminar is personalization techniques for federated learning. Federated learning is a technologies that enable training machine learning models over networks of remote devices, and is a hot research topic nowadays. But training model based on the embedding in local data of heterogeneous device is a challenging task, and multiple personalization techniques are suggested. So in this talk today, I will give you a brief insight into federated learning and embedding training issues. And then I will introduce some personalization techniques for federated learning, and finally, I will present part of my research in this area. Here is my outline. First, I will give a background and about what is federated learning and why we need federated learning, and embedding the training issues of the federated learning. Second, I will present the motivation of our works. Then I will detail our proposed framework FedGroup. And finally, I will give the evaluation and conclusion of our work. Today, with a lot of open source datasets and machine learning codes, we can easily build our AI model. But if we want to improve the model accuracy, we still need more training data. Fortunately, people have produced a large number of the mobile devices, and these devices store lots of the distributed load data. But these data are usually not collected in open source dataset. And if we can obtain this distributed data as training data, it will be a great help to improve the accuracy of the model. Recently, a distributed DNS training framework named Federated Learning it has become a hot topic. Federated Learning provides new ways to solve a big data modeling problem. In federated learning, many clients can collaboratively train a model while keeping the training data decentralized. One of the federated learning application is the query suggestion of the Gboard. Gboard's user can collaborate to train a recommendation model to predict users' typing. Before we go into more detail about the federated learning, I would like to show you a traditional framework first. This is a cloud-centric DNS training framework. And include a cloud server and some mobile device, and each mobile device also cloud client maintain a local training data set. So the workflow of the cloud-centric and training framework is first, the cloud send a data request to all clients, and the client then send the local data to the server, and the server collect this data to make a training data set. And next, the server train a neural models based on the collected data, and then deploy the model to all clients. But usually, user data on mobile devices such as smartphones is private. Users are not willing to allow this data. So even though we have a lot of the data is distributed and cannot be centralized, and that's what we call the data item issue. That's why we need federated learning. Unlike the previous cloud-centric framework, The main idea of federated learning is training the neural networks without centralizing data. This is how federated learning works. First, the servers send the initial global model to all clients. Then each client performs several epochs of the stochastic gradient descent based on their local training datasets. Once the local training is done, all clients send by the gradients. And finally, the server averages these gradients and allow the global model, update the global models. We call above process a communication run, and a complete federated learning training process needs multiple communication runs. The main advantage of this distributed training paradigm is enable the server to learn the patterns from the client's model while providing a privacy protection of the local data. But this raises new issues. In real scenario, the data distribution of the remote device is usually imbalanced. So studying the negative effect of this imbalanced data on federated learning and how to mitigate these negative effects has become an important research topic. So in particular, if we are talking about imbalanced training challenges in federated learning, there are several questions that we may ask about what is imbalanced data and why imbalanced data should be handled carefully, and how to address this imbalanced learning challenge in federated learning. And to answer the first question, I would like to present a brief review of two kinds of imbalance in data. Technically speaking, any data set that exhibits an equivalent distribution between its classes can be considered imbalanced. For example, in our picture, the gray circle represents the majority sample, and the blue stars are the minority samples. There is only one concept in the data space. Obviously, from the aspect of the quantity, there has an imbalance between the majority and minority. We call this kind of the imbalance between class imbalance. A more common scenario is there have multiple concepts in the data space. For example, in the right picture, both majority and minority have dominant concept and a sub-concept. For both classes, the number of examples in the dominant cluster significantly outnumber the example in the respective sub-concept clusters. We call this kind of imbalance is within class imbalance. So the issue of the within class imbalance is the sub-concept may go unlearned by some inducers due to its lack of represented data. This issue embodies the imbalance due to the real instance. Here we show some example of between class imbalance and within class imbalance in the real world. The left picture illustrates the Zipf's laws, which was stating that given some corpus of the natural language utterance, the frequency of any word is inversely proportional to its rank in the frequency table. For example, the frequency of the most frequent word, let is approximately twice as the second most frequent word and. Another example is the video of the public traffic cameras. In most cases, the deployment position of the highway cameras and street cameras are different. The highway camera usually faces the main road, so the captured images are mainly the front and rear of the vehicles. That is to say, the front and rear of the cars are dominant concepts, and the sideway of the car is the sub-concept. However, the street cameras are usually deployed on the public traffic lights at coast roads. So this camera can capture more side view images than the highway cameras. In general, both between class imbalance and within class imbalance are common in real distributed datasets. The second question is, why imbalanced data should be handled carefully? This is because we require a classifier that provide a balanced degree of the predictive accuracy for both minority and majority on the dataset. But we find the classifier tend to provide a severely imbalanced degree of accuracy, with the majority class have higher accuracy than the minority class. Suppose that if 90% of the training samples are labeled CAD, a classifier can achieve 90% accuracy by a naive always CAD classifier, rather than learning the patterns of the training sample. The situation is similar in the federated learning scenario. Due to inconsistent distribution of the client's data, the federated training procedures can be difficult to converge. This is a picture in my previous paper. We show an example in a figure. From the left to right, the non-IID level of the local data decrease. In a high non-IID setting, the discrepancy between the client model and consensus global model is high. The accuracy is fluctuating and convergence is slowed down. But because the federated learning server cannot access the client's private data, it cannot solve this issue from the source. So in the non-IID case, it's difficult for the global model to maintain consistency and personalize. The last question is how to address imbalanced learning challenges in federated learning. Suppose that we know the ground truth distribution of the data and the data distribution of the client A and client B are non-identical. After performing several epochs of local channel, these two clients can get a local optimal solution respectively. However, since the simple averaging these two solutions will yield a terrible result. As shown in the picture, the global model cannot perfectly combine the classification power of this client's model, so the final accuracy degrades significantly. Then there are two ways to address this challenge. First, we can generalize the global model to try to minimize the loss of more potential data distributions. And secondly, on the contrary, we can personalize the global model for the individual clients before we perform the evaluation. Many techniques have been proposed to enhance the generalization ability of the global model. We can categorize these techniques as data space methods and optimization methods. For the data space aspects, there are oversampling, undersampling, data argument, generating model, and client selection, and so on. The between class imbalance will be mitigated if we generate the appropriate amount of the synthetic minority samples. Even though this is a very superficial way, the implementation cost of the data space methods is cheap. For instance, in P2P case mode, each client generates minority samples using smart algorithm and share this synthetic data with each other. We can also apply the common generalization methods to the local optimization of clients such as regularization, meta-learning, normalization for a local approach, state size, gradient, directions, variance, and so on. For example, the Federated add a penalty terms to the local objective functions to reduce the discrepancy between global model and client models. The main shortcomings of these optimization methods are they involve additional hyperparameters and computational overheads. And the performance improvement of this method is unwarranted. Since the global model cannot be well adapted to each client, we can personalize the global model for each client to provide customized solution. The most well-known method is to fine-tune the global model with an additional validation set. Some more technical methods are to interpolate the global model with the local model, or we can connect the global model and a local model with a gating network. I prefer to group these methods into a class because in these methods, each client holds a customized model and don't need to modify the structures of the training frameworks. Another option to improve the personalization is we can cluster the client's training based on the similarity of their tests. In this way, we can divide how to optimize global objectives into several easier sub-objectives. Not only that, those clients with incongruent data distribution can be separated to avoid performance degradation caused by conflicting optimization goals. However, because the clustering approach will introduce the hierarchical structure to the Federated Learning frameworks, it will increase the system complexity. In the rest presentation, I will introduce the cluster Federated Learning and show the details of our work. Our work is an improvement of the previous cluster Federated Learning framework. The left picture shows an example of the optimization for incongruent race function. The incongruent distribution made the model convergent difficulty, and so instead of optimize a complete global goals, we can divide it into several sub-optimization goals. Based on these ideas, cluster Federated Learning managed to group the training of clients based on the proximity between their local optimizations. The right picture is a general overview of the cluster Federated Learning. The training test will divide into multiple subtests to strike a balance between consistency and personalized. Then I will show our the motivation of our works. Previous cluster Federated Learning framework has various shortcomings. For example, the vanilla cluster Federated Learning use a recursive bipositioning clustering strategy, which has a high computational cost. IFCA cluster client based on the loss value evaluate on grouped model. However, to accomplish the evaluation, the server needs to broadcast all grouped model round by round. So the communication is inefficient. Another cluster Federated Learning framework like FEDSYNC use Euclidean distance between group models and client models as the clustering matrix. The shortcoming is the distance concentration phenomenon in the high-dimensional situation. This will significantly hurt the clustering accuracy. Here is an example to show the limitations of the previous L2 distance-based clustering framework like things. Suppose the data we manage to be classified as shown in the picture, and the hypothesis set is the linear model. So we can get one solution of the chi-n A, just like -1 +1 0, and one solution of chi-n B, just like -2 +2 0. The L2 distance between chi-n A and chi-n B is √2, even though their solution represent an equivalent linear classifier. And if we extend this dimension in this example to d dimension, the distance between client A and client B will be √d. This value cannot reflect the true similarity of the classifier. The distance concentration phenomena of the L2 distance is another issue. It will cause the violation of the neighborhood structure, which has an adverse effect on the performance of the pairwise distance, such as k-means, k-medians, and hierarchical clustering. So we propose this is our motivation. We propose a new cluster federated learning framework. The overview of our framework is showing the left picture. There are 4 characteristics of our framework. First, just like the previous cluster federated learning framework, there is no consensus global models. Second, the group may be empty and client assignment is static and one-off. Fed group can handle the join of the newcomer device. We use the mean over the absolute difference of the pairwise cosine similarity to avoid the distance concentration phenomena in the high dimension situation. To further reduce the computational overheads, we decompose the other matrix by truncate SVD before calculating pairwise similarity. It can be regarded as a low-dimensional embedding of the pairwise cosine similarity. So our new matrix called Euclidean distance of decomposed cosine similarity is computationally efficient and has no distance concentration. We also design a new closed-start strategies. Before model training, we need to determine the optimization directions for each group. We use k-means to clustering clients based on EDC and get a mean optimization directions of each cluster centric. Then the servers say these optimization directions for client assignment. If the newcomer join the training network, the server minimize the normalized cosine similarity between the optimization directions and client's pre-trained updates. That is the client will choose the group with the most similar optimization directions. So the main advantages of our clustering strategies is more communication efficient and easily extensible. Then I will show you some experimental results. We implement the Fed group framework based on Fedpro and TensorFlow. We choose the federated averaging, Fedpro, IFCA, Fedthing as our baseline. We use the data set. We use E-means and FE-means as our data set. The results show that the Fed group and IFCA are significantly superior to other frameworks. For example, the absolute accuracy improvement on FE means on means NLP is 4%. The 4%. The accuracy improvement on FE means NLP is 26.9%. Besides, FE things perform worse in all experiments, even lower than the Fed average. This is because the Euclidean distance is not suitable for high-dimensional clustering. The value of the chaining loss of Fed group is lowest in our example, and the convergence speed is also faster. We noted that the experimental result of IFCA and Fed group are similar, but IFCA need to broadcast all groups model in each round. So our clustering strategy is more communication efficiency. The discrepancy results show that there has a trade-off between the consistency and personalized. Maintain the global consensus model like Fed averaging and Fed Pro can achieve lower discrepancy. However, lower discrepancy cannot guarantee higher accuracy. For example, Fed group perform better than Fed averaging. On the other hand, compared to IFCA and Fed sync, the discrepancy of Fed group remain at a low level in the initial rounds, which means our client assignment is more efficient. And so the contributions of our works are we propose an efficient cluster federated learning framework and construct a new data-driven distance measures. And our glucose algorithm is static and efficient. Our clustering strategy can handle the newcomer device. There are many open questions and challenges in federated learning. For example, the client data distribution shift problems. This is my ongoing work. And another issue like the struggling clients should be considered. That's all my presentation, and thank you for your listening. If you have any question, yes.
Thank you, Mo Ming, for a very nice and clear talk. I like it very much. I'll open the floor to everybody. If you have any questions, please just unmute yourself and just ask directly, or if you're shy, you can type in the question. Okay. Maybe I ask one question on behalf of Professor Ping, because he has to go early. He was wondering if you can explain how do you determine the K value for non-IID data silos?
So your question is how to determine the
K value, right? You need to determine the K. Is it maybe the cluster?
I mean K value. Yeah. The K value of my work is presetting.
Preset, right?
Yeah, preset.
Yeah. So, but how do you determine? You just decide on a K value, or how sensitive is your method? Related to the K.
We just use the research to find the optimal value.
Okay. Okay. All right. Any question from the folks? I have a question on your further work. When you say data shift, you mean the data shift over time, right?
Yes.
Okay, I see. Oh, that's very challenging, even for non-federated scenario. What about the second one? I don't understand. What is straggling client? Can you explain a little bit more? Yeah.
Because in class federated learning, we and in my frameworks, we need to do some pre-training work. So we must make sure in the pre-training phase we have enough client to the co-start in the co-start strategy in the co-start. So yeah. If some client quit out, it's be a bit challenging.
Okay. All right. Any questions from the audience? Don't be shy. I guess no question from the audience. All right. Thanks, Mo Ming, for very good talk again. Thanks for preparing this. We look forward to working with you soon. Okay. All right then. Thanks everyone for attending.